And we're back. And welcome to the laboratory. Actually, it's not a lab as much as it's an investigation into motion and the laws of motion, as well as some simple machines that we've been studying in our Chapter 5 of our textbook in 6th grade science. For this investigation, we set up 8 stations. And over the course of the next probably 3 or 4 videos, we're going to go through all of them. This first one, on your paper, identify the numbered objects as either levers or inclined planes. Also asking what else at this table, as we pan back here, might be considered a lever. And looking around the laboratory, can you name at least 3 different objects which are levers or inclined planes? What are they? All right, let's move around. So object number 1 is that pair of scissors. Simple machine, actually it's a compound machine according to our chapter in our textbook, but the primary machine that's at work here is either a lever or an inclined plane. I know I had some students that wanted to tell me that it was both due to the wedges that were used for the sharpened ends, but I want to know what is the machine that's in motion here. So that's the first one. Number 2 is one of these out of the science table, and I'm wanting to know, is this a lever or is this an inclined plane? And we were talking about this in class about what an inclined plane might be. Object number 3, here we go again. Are these inclined planes or are they levers? So we take a good look at them. Inclined planes or levers? Then reminding the students not to touch anything. Here was item number 4. Yes, it is set. Yes, it is ready to go. No, nobody actually stuck their finger in there. Now, the spring adds extra force, but I want to know, is this device primarily a lever or an inclined plane? Let you decide that. Item number 5 can be found in almost any classroom. I'll even come around to the edge on this one. You've seen these before. I'll even actuate it for you. Is that a lever or an inclined plane? Item number 6, right here, it's the microscope, but this round knob thing, is this a lever or is this an inclined plane? Excellent question. And finally, object number 7, right here, we pick this up. We can do work with that, or we can use it this way to extricate. I'll let you look up what extricate means. Where we can extricate something out of there. Is object number 7 an inclined plane or a lever? Now we move over here to station. Oh, the next thing here. What else at this table could be a lever? Well, most students point to this right here. This might be a lever. Now you need to know what we call that. And then looking around the science lab, let me back this up. Oh, I've got it as far back as possible. What else in here might be a lever? Well, as we go around the room, what else might be a lever? There's several items. Now, many students did come in on that right there, the emergency eye washer, because that is one of the 2. I don't know which one it is. You'll have to come off on that one and tell me. Then Some students actually caught that right there. Might be one of them. And then students did ask, and I'll answer this one on the videotape. They said, teacher, what's a drawer? Well, a drawer does not work on an inclined plane, but it is a flat plane. So, I would give credit if you said that that was a flat plane. Now, let's move off to station number 2. Now, station number 2 is our mathematical field trip. Please use the provided formulas to complete the computations at this table. So here was station number 1. Our average speed formula is distance over time, or S equals D over T. We studied that in class. It's time for a field trip. We board our bus and travel 1,500 kilometers from Dexter to the La Brea Tar Pits in Los Angeles. The trip takes 15 hours. What was the average speed of the bus? Make sure and give a complete answer showing the units. Well, if we're going to plug this in, S, speed, equals D, distance, over T, time. So S would equal 1,500 kilometers distance over 15 hours time. So S equals D over T. S will equal 1,500 over 15. So that will give us our average time. And by the way, shameless plug here. If you've never been to the La Brea Tar Pits west of downtown Los Angeles, please take time to go and see the museum and the pits. It is amazing. Station number 2. This one's a distance traveled problem. Distance traveled is speed times time, or D equals ST. So when we're done at the La Brea Tar Pits, we take a side trip to see the circus act at Circus Circus in Las Vegas, Nevada. The trip took 5 hours and the bus traveled an average speed which was 100 kilometers per hour. How far did we travel? Please give your answer with the proper units. Now, it's one thing we're working on right now is trying to get the units in. But again, D distance equals ST. Well, S in this case is 100, T is 5 hours. So D equals 100 times 5. I'll let you do the math on that one. We're also doing acceleration, because that's in the chapter. Final speed minus starting speed over time. The average student in our school has a mass of 35 kilograms. Our bus holds 70 students. This results in a mass of 2,450 kilograms. Because of this, our bus is slow getting going. From a standing start, and I don't know about students in other schools, but students in our school had issues with the term standing start. They didn't realize it meant 0. It takes almost 5 minutes to reach 100 kilometers per hour. What is the acceleration of our bus? Please give your answer using the proper units. So again, let's go back up here to our formula. Our final speed is 100. Our starting speed is 0. 100 minus 0 over time, which is 5 minutes. So it's 100 over 5. And our final station, our field trip to Los Angeles, Las Vegas, and back to Dexter was great. We saw lots of neat things, but it was long. It was 1,500 kilometers from Dexter Middle School, DMS, to Los Angeles. Then it was the answer for number 2 to get to Las Vegas. Finally, it was 1,289 kilometers from Las Vegas back to DMS. How far did we travel on our journey? Please include the units in your answer. This one caused problems for several students because there's no formula here at the top. And hopefully by now you've realized that all you have to do is add up the numbers and come to a final total. And that now brings us to station number 3. This is our first real investigation in this lab. Place the steel ball at the top of the channel and release. What happens? Write a sentence to describe what you see. What force keeps the ball in the channel? Where do you think the ball will reach its maximum speed, or I'm sorry, where do you think the ball reaches its maximum acceleration, its fastest speed? D, try starting the ball halfway down the channel. What happens? Please give your responses in complete sentences. So let me reach in here. Let me pull this back a little bit. There we go. We're going to put the ball up here in the top. Wow. What is it that keeps that ball in that channel? And of course the students could do this for hours and hours and hours. Now I'm going to start this about halfway down. Halfway down. Oh, we ended up in the sink. Let me try that one more time. See what happens. Here we go. Nope. Didn't make it. So we have to come up here almost to the very top in order to get the ball to go around. So what happens? What force keeps the ball in the channel? Where do we think that this ball reaches its maximum acceleration? Is it here at the top? Is it here in the middle? Is it here at the bottom? One more time. What is it about that that keeps it in that channel? We'll let you ponder that. In the meantime, we're going to pause the video for a moment, and then we're going to do 3 or 4 more investigations.